While Rutherford's model was revolutionary in terms of the development of a nucleus, everyone knew that there was something wrong with it. Even Bohr or even Rutherford knew that there was a problem with it. And that was that the electron traveling around the nucleus had to lose energy. That electron would continuously lose energy and would circle in and eventually collapse in on the nucleus. So this thinking of the electron just moving around the nucleus like planets around the sun had to be wrong. So we started looking at evidence for how the electrons were arranged and organized around the outside of the atom. And the person who made the next big leap in terms of the model of the atom was Niels Bohr. And so we had the Bohr model. And what Bohr did was he would take samples of elements, he would use energy to excite those atoms and observe what happened to them. What he found was that each element, each sample of an element, if excited, would give off a characteristic spectrum of colors. So this energy that was given off when you would excite the atoms, Bohr found that light energy was given off when energy was added to samples of different elements. So what we really need to do is take a look at the nature of light. So if we look at 400 nanometers, our frequency is at 7.46 times 10 to the 14th hertz. Energy is 4.94 times 10 to the minus 19th joules. If I go up into the green region here at 500 nanometers, longer wavelength, we end up with a smaller frequency. So we go down to 5.98 times 10 to the minus 14th hertz, and also a lower energy, 3.96 times 10 to the 19th joules. If we then jump up into the red, we are at around 700 nanometers, and again our frequency goes down even lower to 4.27 times 10 to the 14th hertz, and our energy goes down even lower as well to 2.83 times 10 to the negative 19th joules. So a photon of red light is lowest in energy, and it would have a low frequency also, but a longer wavelength. So we can go back and take a moment to just draw let's focus in on the properties of wave just for a moment. You can see from the picture here that if you look at a wave and you measure the distance from one peak to the next peak, or from one trough to the next trough, that would represent one wavelength. The distance from the midpoint of the wave to a peak or a trough would be the amplitude. We can use that very much. And this idea of frequency is, imagine yourself standing at the beach and you're looking down at a pebble and you counted how many waves went by in a minute. The waves per amount of time would be the frequency. Now it turns out that if you look at the units on those, if you take the frequency and you multiply it times the wavelength, that ends up being equal to the velocity of the wave. So frequency times wavelength gives you velocity. The other thing we saw from the website when we looked at the different wavelengths and the frequency and the energy, we saw that as the frequency went up, the energy went up. Well, the relationship that we get there mathematically is that energy is equal to a constant we call Planck's constant times the frequency. So these are the two mathematical relationships that would relate the frequency, the wavelength, the speed of the wave, and then the energy and the frequency. Yes. So here, just to give you kind of a perspective on light, our visible light is part of a larger spectrum called the electromagnetic spectrum. And you see some familiar words in here. If we go to, remember the blue is the higher energy, so the higher energy side in this case is to the left of this diagram. Higher energy from blue is ultraviolet. Those are the rays that we get a little nervous about if we're out in the sun. Higher than ultraviolet, we have X-rays, and those we get so nervous about that the people that are taking our X-rays oftentimes move out of the room. And then even higher in energy are gamma rays. If we look down at the lower energy side of the spectrum, so down beyond red, we have the infrared region. Infrared is heat, more or less. So if you see something that's hot or radiating heat, it's radiating infrared radiation. Microwaves, very low in energy. However, they're of a particularly interesting wavelength that we can use to heat up food. So we can talk more about that in class. And then even down farther, we have radio waves and shortwave FM and AM waves. Obviously, those kind of fill the air. So this electromagnetic radiation has a whole range of energies that go from very, very dangerous and harmful gamma rays to radio waves, which are relatively harmless to us. Back to what this tells us about the atom. Well, when we looked at, for instance, hydrogen, we would get a particular spectrum of colors produced when the atoms were excited. They would release energy or light of certain wavelengths. And so here are the 4 different wavelengths of light that hydrogen would give off. And each element would give off a different color, a different set of spectral lines. So what does this mean? Well, what it means is that if we excite something, so in the picture here, they're showing a lithium atom. A lithium atom in its lower energy state might be referred to as the ground state. And then if we add energy to it, it will go up to an excited state. So that would be the adding of energy. What we would observe is when that atom fell back down to the ground state, and it would emit a photon, in this case a photon of red light, and so it would tell us something about the energy level that the lithium atom jumped up to. So let's take a look at what that looks like. So over on the left there's a light source, and we can control the wavelength of that light source. So I'm going to set it at the 121.6 nanometers. So remember that 121.6 nanometers compared to 102. Well, we'll just do it with the 121.6 nanometers to start with. And if I send the photon through, it hits the hydrogen atom. You see it alters the hydrogen atom. And then if you look at the picture down below, let me send it through again, you can see the photon or the electron jump up from the n equals 1 level up to the n equals 2 level. So these energy levels that are being depicted down here in the bottom are the energy levels of the electrons. Let me do it one more time. So the photon comes in, it hits the atom, the electron jumps up from the n equals 1 level to the n equals 2 level. When it falls back down again, it emits a photon of the wavelength of 121.6. Now, if we use a shorter wavelength, now this would be a higher energy, so you can kind of think, well, if I put more energy in, what's going to happen to that electron that's down in the n equals 1 level? Sure enough, we have it go in there, it jumps all the way up to n equals 3. Notice that it gives off a photon as it falls to n equals 2, and then it gives off a second photon when it falls from n equals 2 to n equals 1. So we're gaining a little bit of information about what's going on in this atom by the wavelengths of light that are given off. Let me send another photon through. Again, it jumps all the way up to the 3rd level. This time it fell from the 3rd level down to the 1st level and gave off a shorter wavelength or a higher energy photon. Let's go and do one more. We'll go down to 97.3 nanometers, so again a shorter wavelength to a higher energy. We're going to send the photon through. Boom, goes all the way up to n equals 4, drops down to n equals 3, sends off a photon, drops down to n equals 2, sends another photon, and then to n equals 1 and sends a third photon. And try that again. All right, and again in the picture you see how the arrangement of the hydrogen atom is changing each time it absorbs a photon. It goes up to that higher energy state, releases a photon, goes down to a lower energy state, can release another photon, goes down to another energy state. In the analysis of this then, Bohr was able to show that these different levels corresponded to energy levels for the electrons. The takeaway for Bohr's model is that we still have the nucleus present, so we still have that nuclear model of the atom, but our electrons occupy particular energies. So in other words, an electron can exist at this energy level or this energy level, but it can't exist at this energy level here. This idea is referred to as quantized or fixed energy levels. And this quantization of the energy levels will lead to what we'll talk about next, which is the quantum mechanical model, quantum wave mechanical model of the atom, which will be the topic of our next discussion.